Hello, and welcome. In this video, we explore how probability works using two scenarios, coin tossing and a Plinko game board. We will see why a seemingly fair process can actually be quite unequal. As a caveat, we don't usually learn good math by watching videos, so please slow down and do some real math on paper or using other tools. In solving probability problems, there is a common illusion that the number of options dictates your odds. The fact is, in probability, true equality is determined by the mechanics of the event, not just the number of final bins or the way we organize the outcomes. So do slow down and think through the processes. Imagine three friends wagering on a single movie ticket using a coin toss. Aiden picks two heads, Cameron picks two tails, and Bill picks a head and a tail. Does everyone have an equal chance? The fairness depends on how we define the rules. If head and tail means getting one of each in any order, the outcome space changes significantly compared to requiring a specific order. When we map the sample space of two coin tosses, we see four equally likely outcomes. Head, tail, and tail head are distinct events, which changes the probability for anyone betting on mixed results. If the rule allows for mixed order, Bill has effectively captured half the board. The game looked fair, but the probability was heavily weighted in his favor. Let's now move on to another scenario, a two-layered Plinko or Galton board. A Plinko board creates a similar physical illusion. Three bins at the bottom might suggest a 1 in 3 chance, but the bins are just final destinations, not the paths themselves. We need to take a closer look. To understand the odds, we must map the decision tree. A marble navigates a series of binary choices, left or right, at every peg. These paths dictate where the marble lands. Different paths can merge into the same bin. The middle bin isn't luckier. It is simply a wider target because multiple path combinations lead there. As shown in the illustration, there are two pathways for a marble to land in the middle bin. Does it sound like the head, tail, and tail head part of the coin tossing problem? Statistically, the middle bin collects half of all outcomes. It is twice as likely as the side bins, despite appearing to be just another equal option. As we add more layers of pegs, the paths continue to zigzag toward the center. This accumulation of paths is essentially the birth of the bell curve. To develop process literacy, follow these steps. Identify the randomizers, define the outcomes, list every single path in the sample space, group your conditions, and count the paths, not the bins. Stop reading the label and start reading the mechanism. Whenever you encounter a seemingly fair game, ask yourself to see the sample space that created those options. Do not trust first impressions. Whether it's a carnival game or a financial model, fairness is hidden in the paths. Always look for the decision tree and look deeper into the problem structure. Now please slow down and think about the common structure shared by the two-coin problem and the two-layer Plinko board. Does it give you a hint at the Pascal triangle? Thanks for watching.